Section: Introduction. In this section, we will discuss the growing compute requirements for training large language models, LLMs. The demand for compute power has been increasing rapidly, with a 750-fold growth every 2 years. This trend has led to the development of AI accelerators that focus on boosting hardware compute power, sometimes at the expense of other components like memory hierarchy. However, there is a new challenge emerging in the training and deployment of AI models: memory and communication bottlenecks. Many AI applications are now facing bottlenecks due to limitations in memory and communication within and between chips and AI accelerators, rather than in compute power. This issue has been observed in the past, with early warnings dating back to 1990 when Ousterhout highlighted the impact of memory performance on system performance. Subsequently, in 1995, Wolf and McKee introduced the concept of the memory wall, emphasizing the critical role of memory bandwidth in determining the speed of operations. Despite advancements in memory technology over the past 30 years, the memory wall remains a significant bottleneck for various AI tasks. The peak compute power of server-grade AI hardware has increased significantly since 1998, while the improvements in DRAM capacity and interconnect bandwidth have been comparatively modest. The memory wall problem encompasses limitations in memory capacity, bandwidth, and latency, posing challenges for data transfer between different components of the hardware. Recent trends in AI models, especially LLMs, show a substantial increase in data volume, model size, and compute requirements. While the compute power needed for training these models has surged by 750 times every 2 years, memory constraints have started to impede performance, particularly in model serving. Scaling out training and serving to multiple accelerators to overcome memory limitations can also face the memory wall issue due to communication bottlenecks between accelerators. Even when models fit within a single chip, intra-chip memory transfers are increasingly becoming bottlenecks, affecting the efficiency of specialized compute units like tensor cores. The disparity between the growth rates of server hardware flops, DRAM, and interconnect bandwidth has highlighted memory as a primary bottleneck, surpassing compute power limitations. This trend underscores the critical role of memory in AI tasks, even when models can be accommodated within a single chip. Section Summary. In this section, we analyze the growing challenge of memory and communication bottlenecks in training and serving AI models, which are becoming more prominent than compute limitations. Despite significant advancements in memory technology, the memory wall issue, predicted decades ago, remains a dominant bottleneck for various AI tasks due to the disparity in memory and compute improvements. The trend shows that memory constraints, including limited capacity, bandwidth, and latency, are increasingly hindering hardware capabilities, even as compute power continues to scale rapidly. Section: Case Study. In this section, we will first explain the runtime characteristics and the performance bottleneck related to transformer inference. We will look at two variations of the transformer architecture: the encoder architecture, like BERT, which processes all tokens simultaneously, and the decoder architecture, like GPT, which processes and generates one token at a time. When analyzing performance bottlenecks, a common method is to calculate the total number of flops needed for the transformer encoder-only and decoder-only models. However, this metric alone can be misleading. It is crucial to also consider the arithmetic intensity, which is the number of flops that can be done per byte loaded from memory. This can be calculated by dividing the total flops by the total number of bytes accessed, also known as MOPS or memory operations. To demonstrate the importance of arithmetic intensity, we studied models like BERT Base, BERT Large, and GPT-2. The encoder models, BERT, involve matrix-matrix operations, while the decoder model, GPT, involves repeated matrix vector multiplications during inference. To identify bottlenecks in transformer workloads on standard hardware, we profiled transformer inference on an Intel Gold 6242 CPU. The analysis included total flops, MOPS, arithmetic intensity, and the final latency of these models for various sequence lengths. It was observed that GPT-2 has significantly longer latency compared to BERT base or BERT large for each sequence length due to higher memory operations and lower arithmetic intensity in the auto-regressive inference of GPT. To overcome the memory bottleneck and continue advancements in AI, we need to rethink AI model design. Current methods are often ad hoc, require large amounts of training data, involve extensive hyperparameter tuning, and struggle with deploying large models for inference. Additionally, hardware accelerators have focused more on increasing peak compute rather than improving memory-bound workloads, making it challenging to train and deploy large models efficiently. Efficient training algorithms are crucial to address these challenges. Second-order stochastic optimization methods show promise in reducing the need for extensive hyperparameter tuning, but they come with higher memory requirements. Strategies like the Zero framework from Microsoft aim to train larger models with the same memory capacity by optimizing memory usage. Techniques such as rematerialization can reduce memory footprint significantly while slightly increasing computation, enabling training of large models on single-chip memory. Designing optimization algorithms that support low-precision training, like using half-precision arithmetic, can enhance hardware utilization. Exploring a mixture of different precision formats may further improve efficiency and memory utilization. These algorithmic innovations are essential for maximizing hardware capabilities and addressing memory-related challenges in AI model training and deployment. Section Summary. In this section, we outline the runtime characteristics and performance bottlenecks of transformer inference, focusing on the encoder, e.g., BERT, and decoder, e.g., GPT, architectures. By studying the arithmetic intensity of operations involved, we compared models like BERT and GPT-2, highlighting how higher arithmetic intensity can lead to faster performance despite similar flops. To address challenges like the memory wall and high training costs, efficient training algorithms and optimization methods are being explored, such as second-order stochastic optimization and reducing memory footprint while increasing data locality. Section: Efficient deployment. In this section, we discuss efficient deployment strategies for advanced models like GPT-3 and large recommendation systems. Deploying these models for inference requires distributed memory deployment, which can be challenging. One way to tackle this challenge is by compressing the models for inference. This can be done by reducing precision through quantization, removing redundant parameters through pruning, or designing smaller language models. Quantization, the first approach, involves reducing the precision of the model. While reducing training precision significantly is difficult, using ultra-low precision for inference, like INT4 precision, is feasible with minimal impact on accuracy. This can lead to a significant reduction in model size and latency. However, going below INT4 precision for inference is more complex and an active area of research. Pruning, the second approach, focuses on removing redundant parameters from the model. Current methods can prune up to 30% of neurons with structured sparsity and up to 80% with unstructured sparsity while maintaining accuracy. Going beyond these limits is challenging and often results in accuracy loss, which is an ongoing research problem. The third approach involves designing small language models, which could revolutionize AI adoption. While the models for small language models have remained unchanged since 2017, scaling data and model size has unlocked new capabilities. Recent work on small language models has shown promising results, especially if a model can fit entirely on chip, leading to significant speed and energy improvements. When rethinking the design of AI accelerators, we face challenges in increasing both memory bandwidth and peak compute capability simultaneously. Sacrificing peak compute for better compute bandwidth trade-offs is a viable solution. CPUs, with their optimized cache hierarchy, outperform GPUs in bandwidth-bound problems like large recommendation tasks. However, CPUs lag behind AI accelerators in peak compute capability due to the focus on maximizing peak compute in accelerator designs. An alternative architecture with more efficient caching and higher capacity DRAM, possibly a hierarchy of DRAMs with varying bandwidths, could bridge the gap between CPUs and AI accelerators. This design could help alleviate distributed memory communication bottlenecks and improve overall performance.